Zhang from CMU.
Thanks for the intro. My name is Zhang. Today I'm going to present a work called AuraSense, where we try to use electric field sensing to enable multiple around smartwatch interactions. This work has been done with my colleagues Junhan, Gierad, and my advisor Chris. Smartwatches are small but powerful computers that becomes ubiquitous nowadays. But their small touchscreens limit what we can do with them. Therefore, many previous projects have been developed to increase the input expressivity of a smartwatch and also expanding the volume of the interactivity, which is also called around-device interaction. For example, a user can control a smartwatch by physically manipulating the bezel, such as rotating, tilting, and clicking. Since our hands are very expressive, we make many hand gestures in everyday communication. Previous work has also utilized hand gestures to control a smartwatch. We can also track the finger position near the device. For example, a user can perform swipe gestures and use a finger as a mouse cursor for selection. It is likewise possible to detect finger touches or track finger continuously on the skin. In these two projects, a user can click on 4 discrete buttons on the skin or use their skin as a trackpad. All of these previous work spills interactions out of the touch screens. However, each system usually can support only one interaction modality. Using electric field sensing, AuraSense is able to track a user's finger throughout the around smartwatch area. This allows us to achieve 3 interaction modalities with a single device. These interactions include gesture controls, in-air finger tracking, and on-skin touches. AuraSense enables 6 interactions. First, we can support discrete buttons on the skin. This could allow us to use the limited screen space for more content. All our demos we built were on top of LG Watch. AuraSense can also support continuous inputs such as a slider on the skin. Likewise, it's possible to do 2D touch tracking. AuraSense is also possible to track the finger in the air. When we experimented this, we found it's also possible to do hand gestures. For example, if you tilt your hand like this, you find the hand to be in the path of electric field, which will cause the signal to change. It is also possible to detect gestures performed by the other hand. To sum up, AuraSense supports on-skin buttons, sliders, and trackpads. It can also track in-air fingers for radio input and do hand gesture recognition for both hands. Before we go through the implementation details, let me first explain the sensing principle here. Our sensing principle is based on the electric field sensing, more specifically, the shunting mode. This technique has been previously utilized in HCI applications by Zimmerman, Smith, and Gogg, and others, though it's never implemented in a smartwatch form factor. In the shunting mode, when a grounded object such as a user's finger enters an electric field, a fraction of the current is shunted to the ground. This introduces a disturbance of the electric field. Therefore, by carefully placing the receivers at different places, we can probe this disturbance and thus track the finger. Here you can see the signals from 4 receivers we placed at the 4 corners of a smartwatch. Note how the signal changes as the finger moves. In particular, the signal increases when the finger is near to electrodes. Using this raw data, we can enable different modalities. Now let's talk about implementation. The placement of antenna electrodes is very important for electric field sensing. The location, orientation, size, and the shape of electrodes defines how the electric field is projected into space. By varying these parameters, we can create designs that are more sensitive to certain interactions. To explore this, we tested a wide variety of antenna designs, seen here. In this illustration, black indicates the watch face, gray represents the transmitter, while red indicates receivers. So we are looking at the smartwatch from the top. All of these antenna designs had one transmitter and 4 receivers. Through rapid prototyping and testing, we found 4 designs that are best enabled the 6 interactions that we showed before. Here are those 4 antenna designs as in physical prototypes. Each antenna design can support certain interaction modalities. As I will talk about later on, there are ways to combine them together to make a meta configuration. Note, in all prototypes, transmitters are right underneath the receivers, since we found this configuration yielded better signal-to-noise ratio. Here, you can see a side view of the antenna design B, with electrodes wrapping around the 4 corners. We connected the electrodes to the electro field sensing chip, which combines a signal generator, analog front-end, and ADC. We connected 1 transmitter electrode to the chip, which projects 115 kHz square wave into the air, with 3 volt peak-to-peak amplitude. We also connect 4 receiver electrodes, each of which has at least 10 by 6 millimeter area. The raw data is then fed into a machine learning pipeline in order to implement interactions. We use 3 groups of features: 4 raw inputs from the 4 receivers, 4 statistics features such as mean, max, average, and standard deviation computed using the raw input, and 4 normalized data points using the mean and max. This process yields 12 features in total. For discrete interactions, we use SMO classifier. For continuous interactions, we use SMO reg regression. To evaluate AuraSense, we conducted a user study. We invited 10 participants, which were right-handed. So we put the device prototype on their left arms. For all following evaluations I'm going to talk about, we first collected 3 rounds of data for training, and then performed a live testing round. The classification or regression result for each trial was recorded in real time. To support buttons on the skin, we use Design H, which has 2 electrodes on each side. For the evaluation, we marked the participant's arm surrounding our prototype watch with a washable marker with crosshairs. In addition to the 4 buttons, there was also a no-touch class. This 5-label classification achieved 92.7% accuracy. AuraSense can also support sliders on the skin. In this evaluation, we use antenna design F, which has all electrodes on the one edge. We drew a 40 millimeter long line on participant's skin, parallel to the left side of the smartwatch. This result indicates a mean distance error of 2 millimeter. Likewise, AuraSense can also track a finger's 2D location on the skin. We drew a 3x3 pattern of crosshairs to the left of the watch with a grid spacing of 10 millimeter. In this case, 2 SVM regression models were implemented, one for x-axis and the other for y. The result reveals a mean distance error of 7.2 millimeter. It is also possible to use AuraSense to track in-air finger movement with radial coordinates. In this evaluation, we used the antenna design I, which has 4 electrodes on the top face. We asked the participant to position a finger at one of 8 possible angles, roughly 3 centimeters away from the watch face. This result indicates an average angular error of 18 degrees. With the same antenna design, it is also possible to detect hand gestures. Our result shows an accuracy of 82.8% for 4 hand gestures plus no touch. We also use AuraSense to detect hand gestures performed by the arm, which wears the watch. Antenna design B, which has electrodes on the corners, is used to support this interaction. The result shows 88.8% accuracy. So here again are the 4 antenna designs we explored. As I noted earlier, certain antenna designs are better suited to particular input modalities. In the other word, no single antenna design can support all the interactions. But this is not ideal because we ideally want one device that can achieve everything. So we built a watch face with 10 electrodes, merging design elements from designs I, B, H, and F. We then built a custom board that can dynamically select which of these antennae are active. In turn, allows us to dynamically create different electric field projections. More specifically, an application can request that a certain configuration being active. For example, a timer app might request a radio input mode. For this setup, we are able to support 4 out of 6 interactions. And of course, we can refine this configuration and support all 6 interactions. Like many other techniques, AuraSense has limitations, some of which is in line with other electric field sensing approaches. For example, it is sensitive to ambient noise, such as fluorescent lights, or other electromagnetic interference from other appliances. We also found the sensor chip sensitive to temperature change, causing a signal to drift when a user first puts on the device. We attempted to compensate for this by normalizing signal in our feature set, but it's not perfect. Finally, AuraSense has a short sensing distance, a few centimeters. This means our system is not disturbed by other activities farther away from the smartwatch, which is good, but it also limits the volume of the interactivity. Thank you. This is AuraSense. I'm happy to take questions.
Any questions?
Really neat work. What you were showing, it looked like the antennas were only on the watch itself, but the watch, of course, is held on by a band, and I was wondering if you had thought about putting antennas on the band enabling gestures that could also be concealed by being done on the underside of the wrist, where other people might not be able to see them.
That's a good question. So when we developed AuraSense, we found attaching electrodes to the top face being most efficient. That's because the arm we put on the device will shunt part of the current as well. We want to avoid that. So when we develop these device prototypes, we carefully place the electrodes only on top, which is on the watch face, to project the electric field only on top of the device, rather than on the band, so it'd be mostly absorbed by the watch arm. So we want to avoid doing that.
I see. Even if we're on the outside, not touching the skin?
Yes. So yeah, we want to keep the position of these electrodes to be as upper as possible.
Okay. Thank you.
Any questions?
Yeah. Hi. Very cool project. I was curious for the angle detection. It seemed like the error was rather large. Do you have a sense for how much of that is due to your system or just people estimating angles poorly?
So the interval, as I said, we trained 8 angle. Each angle has, so between 2 angles there are 45 degrees. That's how we train the system. And when we test the system, we found 18-degree error. I suspect if we train the system better, for example, like using a more or denser training grid with more training positions, it could lower the error. Also, with 18-degree testing error, we are able to support a lot of interactions, such as rotating, like set a timer. But I agree with you, to commercialize this technology, we definitely have a long way to go to decrease the error.
I think one more question. Hello, I'm Yo from St. Andrews. Very nice work, and I have two quick questions. Sorry. If you extend on this work in the future, will you be able to detect the micro finger motion, like maybe two fingers rubbing each other on top of the watch? And the second question is, I realize that you don't have a demo session, so will you be able to try out the system like in the coffee break or something? Thank you very much.
Oh, thank you. So I think in future it's possible to detect fine-grained gestures, but we have to think very carefully about what material to implement the electrode, the size of the electrodes, also the number of electrodes. Also, as I said, electric field is a close-range sensing approach. It's very sensitive to coarse hand movement, but for fine-grained gestures, for example, or fine-grained finger locations, I think we need to explore more possibilities such as different like frequency or different antenna designs, but it's totally doable.
Let's thank Zhang for the presentation.